how does the Earth generate its magnetic field?
Okay, so the Earth self-generates a planetary scale magnetic field in its core. So let me first mention that here's Earth. We live right there, and that's us not to scale. Right now our head is far out in space, right? We would quickly perish. But here's our planet, and if you cut a cross-section through it, the inner half is actually predominantly liquid metal. However, the pressure gets so high in the middle that the innermost third has actually solidified. So this part's solid, this part's liquid. It's all predominantly iron with some nickel and some other stuff. So let's say it's mainly iron, nickel, and other stuff. I'll for today just say sulfur. Could be a couple things, but we'll choose sulfur. Okay, so here's our planet. We've got, for the most part, solid silicate in what's called the mantle. And this core is about the size of Mars. It's big. It's the size of other planets. And it's predominantly, volumetrically, it's predominantly liquid. And this planet, our planet, all planets, are radiating heat out to space. And that causes the mantle actually to be overturning.
But if it's solid, how is it overturning?
It's overturning on about a 500 million year time scale. It's solid state convection. This is the beauty of plate tectonics. It's a whole nother story. But the mantle is overturning roughly every 500 million years. Really slow. And yet we can map it all out. It makes a lot of sense. Okay, so very slow overturn of the mantle. That, though, is allowing heat also to escape from the core. So the core is cooling down as well as the mantle. And as the core cools down, one of the most interesting things is that as the temperature decreases, the inner core grows outwards in time. So this inner core is freezing from the center outwards. It's like an inverse candle. It's actually freezing outwards. It's crazy. And what else is interesting is the inner core is almost purely pure iron. So when it freezes, it's releasing a lot of this light sulfur, or whatever that extra element is, at the inner core boundary. That's what it's called. And so you're releasing light material here, and it's floating up, and you've got convection in the outer core due to the, predominantly right now, due to the freezing of the inner core. There's also cold stuff falling down from here, but we're going to say, for various reasons, as the inner core forms, you drive a lot of turbulent convection in the core. Okay, so crazy weird planet, onion structure, inner core growing outwards. Now, where's the magnetic field come in? Well, okay, so here's our core again. The large-scale magnetic field looks a lot like a dipole magnet. It's tipped a little bit off, but it's not far from the rotation axis of the Earth, about 11 degrees over. Okay, so roughly an axial dipole. It looks from the outside somewhat like a giant bar magnet, except when you look in detail, everything's moving around. We see all these little flux patches, and they're all trucking around fairly fast. So it's not some big static bar magnet, but it does have a similar structure. Most of the energy is in what's called the dipole, the bar magnet part of the field. Okay, so now we've got some magnetic field in this liquid metal. What's amazing is the liquid metal is convecting fast enough. So let's just worry about this piece right here. So there's some fluid motion goes in the region where this magnetic field is. It will actually stretch it and drag it off to the side. And when it does, it actually generates new magnetic field. So the magnetic field gets trapped in the fluid in Earth's core. And the motions of the fluid then drag the magnetic field and generate more magnetic field. So if the fluid motions generate magnetic field through this stretching effect faster than the magnetic fields diffuse away due to the resistance of the metal itself, then you can get a magnetic field. And so if you imagine this flow is going really fast, oh man, it might wrap the field into a couple of big loops. Okay, so maybe there are huge loops of magnetic field inside the Earth's core, and actually we expect there to be. And now if there are other motions that twist these the other way, then you'll get other loops, and other loops, and other loops, and they may all add up to creating a large-scale field. So it's a big turbulent process where we're constantly dragging the field around faster than it goes away, and if we do so in the right way, we'll generate this axial field. Here's some solid inner core. And now let's imagine we just have a magnetic field line wrapping around in a big loop.
Where's that magnetic field coming from?
Along some line of latitude. Let's start by just imposing some torus of magnetic field.
Okay. That's fine.
I'm being very friendly to
We've got
myself.
initial conditions.
Yep. And now let's take a flow that moves upwards and that also has a little rotation to it. So it's a little helical motion. What's it going to do? It's going to take this magnetic field, it's going to get stuck in the flow, and it's going to make a little loop out of it. Well, anytime you have a loop of magnetic field, that means I can draw a little current vector through it. Right?
This is so unusual because normally I think of the current and then I draw the magnetic field of the current.
I think the other way. So now, let's let there be a bunch of these little helical plumes everywhere. What will we do? We'll generate a bunch of these little loops all the way around, and they will spawn little currents, and if we get it right, we'll form a large-scale ring then of current. If we add all these up, that large-scale ring of current is then going to produce a large-scale magnetic field coming through it. So we can have little motions, but if they're organized correctly into a bunch of helices, for example, then we might expect to generate large-scale currents. That will be fairly well organized and will generate large-scale magnetic fields. So let's figure out why might we have helical flows in our system. And the answer is that it's really, you can think of it almost as ice skater theorem for angular momentum. Whenever we get a plume, let's say leaving, for instance, the inner core, the material actually, when it enters that plume, it comes in from both sides. Well, when it comes in from both sides and erupts upwards, that's really the ice skater pulling its arms in. It's in a rotating system, and now the plume has kind of stretched vertically, the fluid. Well, when it does, it causes it to spin. So when the fluid goes upwards, it tends to acquire a net spin in one direction or the other. Well, that's a helical pattern. So you naturally have helices when you have rapidly rotating convection. And so what do those helices do to some background field? Yeah, they typically generate a lot of fairly well-organized little current patches. And those can all add up, we hope, to large-scale fields. And actually, I have one side note. The first person who proposed a fluid dynamo was Elsasser. Back in the, I think he first proposed it in the 1950s. He took the idea to Einstein and said, what do you think? Nothing else works. How about a fluid magnetohydrodynamic dynamo in the core? And Einstein said, oh, it's messy. You're wrong. And Elsasser was very sad. But about 60 or so years later, no, he was right. He nailed it. It's just complex.